Thank you. So yes, I just completed my honors on this work and graduated last May. So it was a great project to be a part of, and I'll tell you lots about it. There was a lot of people involved in the process, so I'll give lots of thanks to them at the end. But to get started, this project is an exploration of Nova Scotia thermomechanical wood pulp for mass production. And so the need for this project came from the pandemic. Even prior to COVID-19, we were using 300 million tons of plastic being produced globally each year. And now it's approximated that we're using 3 million masks per minute. So the output is astronomically high. So currently there's no official guidance on how to recycle masks, leading to more plastic accumulation in our landfills. And the breakdown of the common plastics used in this PPE takes 20 to 30 years. So it's a long scale. What we're trying to do in this work is see if we can use thermomechanical pulp, or TMP, to develop a 100% wood pulp N95 respirator. Now, this is a discovery research-based question, and to jump to the end of it, we didn't quite develop something that is 100% this, but we hope that this work will contribute to the literature and hopefully one day allow researchers to meet this goal. And so to start the project, I looked at what current masks are made out of to gain a better understanding of what we're trying to aim towards. So usually an N95 mask, for example, is made out of multiple layers. The outer and inner layers mainly function to protect the filter. So those help to prevent moisture from getting at the filter and decreasing its efficiency. There can also be support layers that add rigidity and structure, and then the filter layer is more so the active component that blocks out small particles. So typically the plastic used in this is a polypropylene. They can also use polyesters to help in stopping the transmission of water into the filter layer in the inner and outer layers. Also, N95 masks only need to allow for one-way filtration, so they can also include things like ventilator fans that make it more comfortable for the wearer, but essentially only provide protection for the wearer from the environment and not necessarily the environment from the wearer. So looking at what I characterized, I looked at two different types of N95 masks here, as well as a disposable mask. And you can see electron microscopy images of their filter layers. And so what I saw was that they all have this web-like arrangement of very thin polypropylene fibers. I characterized the functionality of the different layers of the masks to determine what plastics were present. And I did see the majority of the time that the filter was this polypropylene, and that we would occasionally see the outer and inner layers being a polyester. And so moving forward in our investigation, we're looking at how we can create these different layers and what types of modifications are ideal to happen to our wood pulp so that these can be replaced with biodegradable alternatives. So starting off with no modification here, we're just looking on the left at a piece of essentially filter paper made in our lab from pressed thermomechanical wood pulp. And so this wood pulp, it has thick and thin fibers. It looks very different than the synthetic version on the right of an N95 filter. You can see that the average width of the fibers is much larger and a lot less uniform. And so we're looking at modifying this and seeing how we can ideally get closer to what we're seeing used as a filter currently. And so in order to do this, we have to understand what we're working with. So wood pulp is complicated in what it's made up of. So it comes from trees, and it's mainly made up of cellulose, which you can see the chemical structure of in this bottom left corner, and then lignin. Lignin can be kind of tricky to work with because its structure is different from every plant that it comes from. So I have a proposed structure of what lignin could potentially be on the right here. And what we know is that it's always made up of these monolignals, which break into these fragments and always connect together through 7 different types of bonds that are highlighted in different colors here. And reactions to remove lignin from wood tend to favor reacting with the beta O4 linkages, because there's a lot of ways that those can be targeted to help break down lignin and remove it from biomass. And so our work looks at if lignin is advantageous to be present, how to remove it, and what happens once it's gone. And to break that down in more simple terms, the paper making process isolates the lignin as well as hemicellulose and other oils and waxes from the paper, beats it and refines it, and then goes on to their wet end paper making typically. And so what thermomechanical pulp is it uses more the beating and refining and a higher energy input versus a chemical modification. So a lot of pulps are referred to as craft pulps. They have a more chemical-based intervention in trying to go through the pulping process. And craft pulps are what we currently see being incorporated slowly into personal protective equipment. We sometimes see these in these support layers of masks, civilian face masks, as well as some other biodegradable components I'll touch on soon. And when we look at thermomechanical pulp, it doesn't have this harsh chemical effluent that goes into the environment that craft pulp has. So we want to try and encourage using this more. And so we partnered with Port Hawkesbury Paper to see how their paper compares to what's currently being used and how it has its own advantages. And so I want to test its ability to retain small particles to see its potential as a filter. I didn't have any aerosol testing available early on in my honors, so I first looked at its ability to capture small fluorescent beads. And so inherently, this is not going to give you the 100% filtration that you're looking for because a wet filtration method lowers the filtration efficiency of a material, which is why we have those inner and outer layers that protect from the filter getting wet. But this did allow for some comparison to see what was creating a better filter and what would retain more small particles when they pass through. So to look at this method, I used a fluorimeter to measure the intensity of a blank sample, compared that to a standard with known concentration of 300 nanometer fluorescent beads, and then filtered that through my test filter sheet made out of the thermomechanical pulp, and then looked at the fluorescence intensity of what filtered through. So we could see how many of those 300 nanometer beads were being retained by the filter based on the new fluorescence intensity and calculate a filtration efficiency based on that. And so looking at this, I just want to point out the key things that we took away from it. So we were basing it more of a comparison between these results. And so what we found was that more densely compact fibers were able to capture more particles, and that the calendar product that we looked at, so we looked at all different parts of the production line, but as we neared the end and they went through more processing and the paper was more densely compact through a calendaring machine, we found that it was able to filter at a much higher efficiency with a much lower thickness. So it was filtering at the same efficiency as something 6 times as thick as this product. And so this led us to suggest that calendaring and further mechanical interventions could perhaps be advantageous for creating a filter down the line. Then we looked at removal of lignin. And to not get too complicated, we used deep eutectic solvents here. And essentially what those are is that they mix 2 solid components together. And when these 2 solids are combined, they become a liquid when at the right temperature and proportion. And then you have both your solvent for your reaction and the reactants that are going to be taking part in it. So those become one thing. You don't have the solvent waste at the end of the reaction that then becomes a harsh chemical effluent into the environment that you see with a craft pulping process. And so that's why we went this route of chemical modification instead of what's typically used for lignin removal. And we use these much more environmentally friendly reagents in this process as well. And so we found through confirmation with many titrations and UV-vis and infrared spectroscopy that we were removing lignin using this treatment, but we found that the removal of lignin actually did not increase the filtration efficiency at all. In fact, in many cases, it did decrease it using the fluorescence testing here. It's known in the literature as well that lignin has antiviral and antibacterial properties, and high lignin content pulp, as a result of all of this, appears to be more advantageous as a filter layer than perhaps its alternative lower lignin content craft pulps. So this is potentially where we could see a role for thermomechanical pulp as it stands, but it needs to increase its filtration efficiency. And so I looked at aerosol testing next. So what I used here is a port account instrument, which I connected to a vacuum pump to blow air in, simulating a person breathing in. So that I was pulling air from the environment, and I used a particle generator to generate a known concentration of particles in the environment around the instrument. And then this looks at two elements. It looks at the face seal leakage around a mask and the particles passing through the mask. And so I used clay to seal a reusable respirator to the face of a mannequin so that I wouldn't have any leakage around the mask. And then I attached two filters. So you'll see me refer to filter 1 and filter 2. And filter 1 here you can see is one of my filters I created. And so I can attach anything I want here without removing the respirator from the mannequin face. It just twists on so that I'm maintaining the same seal throughout the experiments. And you can see that the setup allows for a high fit factor. So what the fit factor is it's a combination of the face seal leakage and what's passing through the filter. And a passing fit factor is considered to be 100. And so it gets a lot higher very quickly. It's an exponential scale when it's measuring it. And so the fit factor passed, showing good face seal leakage, as in there wasn't any leakage in the face seal for the two registered filters that I tested. So these were P100 filters. And then I ended up doing one certified filter and one of my own filters so that I could compare higher values to see what would be a better recommendation for further modification. So just developing a good starting point, not necessarily saying that you should be using this right in this moment for mask material. And what we saw with this again was that the calendared product produced a high filtration ability when compared to other parts in their production line. And we also saw that the deep eutectic treated material had a lower filtration ability. So this shows that removal of lignin may not be that helpful in the filter layer again. And so moving into the other side of a mask, you have the outer and inner portions, which are made up of different things besides the filter, right? So currently medical pulp is used in some of these support layers. It's used in isolation gowns. It's also used in some biodegradable bedpans. So it's been used in medical settings before. And medical pulp, as I was able to take a look at, is its fibers are thicker. So on the previous slide here, this is an image I took of one of the support layers of a mask that's already made with medical pulp. So it has much thicker fibers, more comparable to that we already see with the thermomechanical pulp. And so it would require less modification in terms of the fiber's actual morphology to be used in the same way as the outer and inner layers. As well, it contains lignin, which is a hydrophobic molecule, which would help in preventing the moisture and getting into the filter layer. Having a lower lignin content, though, will help in having more rigidity and strength in these support layers. So looking at more of the removal of lignin in this outer and inner layer versus the filter layer could potentially lead to development of this mask down the line. So just breaking down those two different goals, we see that the structure is already quite good for creating this medical pulp and outer layer, and it's something we recommended that our partners at Port Hawkesbury pursue further. So a new production line for their pulp is looking at how they can start getting into this business, but the filter layer is something that still requires a lot more research and development to be able to filter at the needed level of 95% for 300 nanometer particles. And as I said, there was a lot of people involved in this project, so this was my honors work. And throughout the summer, since COVID was happening, a lot of people's projects were put on hold and they moved on to helping with this. So we had 2 master's students, a research associate, an undergrad, and myself. And we had 2 supervisors as well. Dr. Brousseau's on this call and Dr. Singer as well. So it was a really great collaboration as well with Port Hawkesbury. So I just wanted to make sure I thanked everyone for all the work that they put into this. There's a lot more that went on behind the scenes as well, lots of trials and errors in getting into this field of chemistry. And so I just want to say a big thank you, and thank you to all of you for listening. I'll take any questions if there's any time.